Right.
Morning, everyone, and thank you very much for joining us for our webinar series. And for this webinar series, we will be doing the boiler house design webinar. And so today's session will be presented by both Spirax-Sarco and our guest speakers. And we can just put this next slide. So our guest speaker or our speaker for Spirax-Sarco will be Nick Wisby, and as you know, maybe most of you know, Nick is a results-oriented technical sales support engineer. Quite a rich background in engineering industries, over 2 decades of experience in technical application, electrical engineering, control and instrumentations, and STEAM, and he's been part of Spirax-Sarco for now over 7 years, and is currently based in our Spirax-Sarco office in East Africa, here in Kenya. And I will be your producer, Anthony Macharia, and also Cornelius Schneck, and we will be guiding you through this and answering your questions towards this presentation. So, and our next speaker, I'll hand over to Alvin, who will introduce our guest speakers for now.
Hello, everyone. Good morning. My name is Alvin Logelia. I'll be your guest presenter for today for the Bosch industrial boilers. With me in the call will be Duncan, who will join later on. Back to you, Tony.
Yeah, all right. So our usual housekeeping rules. This session will be about 2 hours long, with about 30-minute Q&A thereafter. And because you'll be quite a lot of people, so all the microphones will be muted throughout the session. And you will be able to submit questions through the Q&A panel function, which can be found on the webinar's dashboard. Yeah. So questions will only be seen by the hosts, that is us, and it may not be possible to answer every question during the Q&A, but we will ensure that we will get back and answer all of your questions through email if we will not be able to cover all the questions that you ask at this time. So we will also just go to the next slide. I would like to show on there how to answer the Q&A. So if you look at on your right, you'll see a live event Q&A session where you will be able to type in your question in the compose box and then click select send. Yeah, if you want to ask a question anonymously where you don't want to show your name, just click and select post as anonymous before you send it, and then you send it. Yeah, we will be able to see it, and then we will be able to publish for everyone else to be able to see the questions that you asked. Yeah. Okay. So, and with that, I would like to hand over to Alvin to start off our today's agenda and take us through the rest of the webinar.
Hello all. Again, my name is Alvin, project manager for East Africa market. Receive greetings from all Africa Industrial Boilers team. For today's training, we're going to speak on modern solutions for efficient generation of process steam, and I believe we can start off. Next slide. So just to introduce Bosch brand itself. So Bosch is a global company with 1% being owned by Robert Bosch GmbH, 5% being owned by the family of the founder, Robert Bosch, and 94% being owned by charitable Robert Bosch Foundation. We have subsidiaries across the world with 468 subsidiaries, and we have a very big workforce as for the Bosch in general, almost 500,000 employees. Next slide. Yeah, so Bosch being a big organization that has invested in various areas, specifically in 4 major areas: energy and building technology, which deals with supply of thermal security and communication technology, building solution and building solutions. And then the second group is mobility solutions, which these will be OEMs and aftermarket automotive spare parts. Industrial technology, where the industrial boilers team lie, and consumer goods, so there are power tools and home appliances, which I'm sure a majority of people know Bosch through. Okay, next slide. Yeah. So the industrial boiler business is pegged under Home Comfort Group under Bosch, and under Home Comfort Group we deal with heating, cooling, home comfort, and process heat, where the industrial business is in. Next slide. Now on to industrial boilers itself. So we are a German company with German manufacturing. Headquarters are in a town on the south part of Germany, town called Gusenhausen. The town has the name Luz in it, which was the former company bought by Bosch, now rebranded to Bosch. We also have another manufacturing plant in Austria, which one deals with hot water boilers alone. So all equipment when it comes to hot water boilers and steam boilers are produced in Germany and Austria. Next slide. So on to Africa, we have a presence across the continent. We have an office in Kenya, which deals with the East African market. We have a partner in Egypt by the name Catex, which deals with Egypt and South Sudan region. We have 2 offices in North Africa, one in Tunisia and another one in Morocco for industrial boilers. Then we have 2 other offices in the West and Central African region, that is in Ghana and Nigeria. Then we have a new office in South Africa, which deals with the southern market of Africa. So yes, Bosch industrial boilers is covering the whole Africa market. Slide. So we do supply around 1,000 boilers a year. That's across the world. The industrial boilers factories have almost around 700 employees above, and we do deliver boilers across the continent to around 140 countries. Okay. Next slide. Okay. So on to our portfolio. We do hot water boilers with boiler capacity being 1 megawatt up to 38 megawatts with a max pressure of 30 bar, max temperature of 225. We also provide process steam with the lowest capacity being 0.2 tons, being biggest capacity for a single boiler being 55 tons. Maximum temperature for superheated steam being 300 degrees, and the maximum design pressure being 30 bar. We also offer components around the boiler house and so on. Things like pumps, condensate modules, water service modules, and other aspects inside the boiler house. Next slide. Okay, and for today's training, we want to look at efficient generation of process steam, and I would love to divide this into two sections, where we have the first section being reducing fuel consumption and CO2 emissions. Then the second part being increased automation, reliability, and longevity. And just looking at the different slides and different components inside the boiler house, where we can actually reduce fuel and reduce fuel consumption and reduce CO2 emissions. We're going to talk about flue gas heat exchangers, condensing heat exchangers, and so on. Preheaters, water coolers, heat recovery modules, TDS controls, and so on. Vapor coolers, speed controls, O2 controls. And then on the second section, we have water service module, boiler controls, water treatment, feed water regulation and pumping, steam accumulators, fuel supply accessories, and the last part, steam distribution. Next slide. Okay, just to kick off the discussion, look at the numbers in Germany where we're doing manufacturing. Around 22% of total energy consumed in Germany as of 2018 figures is used in process heat. Okay, and around 29.5% is in industrial region or zones. Next. Okay, and just looking at Germany as a first world country, around only 20 to 30% of industrial use the best available technology in their system. Okay, around only 17% of the plants use the state-of-the-art technology. Okay, and next slide. So my presentation I've divided into three sections. Again, there's a flue side, flue gas side, there is a burner side of the boiler, and then heat conduction and heat radiation. So the first part, you're going to kick it off with optimization possible on the flue gas side. You can go to the next slide. Okay. So when it comes to measuring efficiency of a boiler, there are two ways which you can measure efficiency. The first one being the direct method. So the direct method is where you look at the calorific value of the fuel that you're burning, of fuel you're burning, and also comparing it to the amount of steam you're producing. Okay? For Bosch, we use the indirect method. Here, which is on the screen, here you look at the boiler efficiency from 100%, then you take out losses in the flue gas, and then you take out losses in conduction and radiation losses. Then from there you can get your final boiler efficiency. Next slide. So just the first section, losses in the flue gas. We have an equation which governs losses in the flue side, and looking at the parameters in the equation, the first one being actually the losses themselves. Then there's a factor depending on fuel, there's the CO2 max, which considering our topic today of efficient steam generation, we cannot really remove or reduce the amount of CO2 unless you're reducing the amount of fuel you're burning, but CO2 will definitely be constant. Then the second parameter is oxygen. is the amount of oxygen that you get on the flue gas. And then the last parameter, last two parameters are the temperature of the flue gas, and then comparing it with the relative air temperature with the surrounding. Next slide. Yeah. And just to kick off the discussion, so on the flue side alone, you can get savings of around 5 to 7% on flue gas losses, and above 5% on heat recovery. Okay? So for Bosch, we do offer flue gas savings potentials when it comes to both economizers and condensing economizers. And we're going to look at the different ways in which, as a company, we do things when it comes to savings, when it comes to the flue gas. Next slide. So the first way is using an economizer. For Bosch, is called an eco. So here you will have your boiler, your standard boiler. You will have your water service module. You will have your feed water pump. You will have your chimney, together with a boiler control indicated as BCO. So in a setup where we have an economizer, water will flow from the water service module, feed water tank, through the feed water pump and into an economizer, which is a heat exchanger, and heat will be moved from the flue gas which is leaving the boiler and into the water that is going into the boiler. And there you're actually saving some fuel by heating up the water that is going into the boiler. For some topics, I'm sure Nick has mentioned on previous trainings, water will be moving from the feed water tank at a temperature of around 85 to 90 for partial deaeration, 103 to 105 for full deaeration, and into the economizer. Then from the economizer, you'll have water at a temperature of 130. Then if you're operating a boiler, let's say a 10-ton boiler operating at 10 bar, the temperature of the water inside the boiler will be around 185. So just by collecting heat from the flue gas, you've already reduced the temperature gradient of the water that is coming in, and the temperature of the steam that is leaving the boiler from your normal, let's say 85 to 90 for partial deaeration, and you've actually pushed it to 130. Therefore saving you around 5 to 7% on fuel. This setup on the screen shows a setup of a pump which has speed control. So the pump will be able to modulate the amount of water that is flowing into the boiler and into the boiler through the economizer. Next slide.
Yeah, I don't know if you want to ask if there's any questions at this point.
Anthony, are there any questions?
Yes, we can go for the first question. Is for the indirect efficiency method, how do you ensure that the data used is accurate for the energy loss in the flue gas and radiation in the field?
So when it comes to data accuracy, this is really dependent on the tools that you're using to measure the losses. Maybe a flue gas heat analyzer must be quite accurate and calibrated. So when it comes to measuring on the efficiency, we are really keen on the equipment that we use and make sure that they're properly calibrated. Although we can do both measurements, both indirect and direct method. as one as a check for the other. Any other questions?
No more questions, and encourage guys to do please answer the questions, and we will be able to answer them as we continue. For now, we don't have any other questions, so we can proceed.
Okay, thank you, Nick. So I think previous, just go to the previous slide, Nick. Okay.
We're past
so,
it, or
no, just the previous one. So on this setup, as you can see, there's a slight different with the previous slide. Here is a setup with the on-off pumps and modulating three-way valve. So water will leave the feedwater tank, flowing to the modulating three-way valve from the pumps. So the three-way valve will actually detect the amount of water that is flowing into the boiler. Okay, and with this modulating three-way valve, you can actually control the amount of water flowing into the boiler through the economizer with on-off pumps. Okay, next slide.
Alvin, maybe before we proceed, there's some questions that have come, and let me just ask them. So the second question is, may your economizers be fitted to any stack, or is it on Bosch boilers stacks?
So currently we are doing it on Bosch boiler stack, but there's a development for other boilers. Yes.
Thank you. And there's another question is, how do you avoid the effects of sulfur dioxide formation whilst using an economizer?
Okay. So sulfur dioxide usually is common when you're burning heavy furnace oil, heavy fuel oil, HF4. How do you avoid it? Usually any fuel will have a dew point where ideally for let's say 2% would be around 130 degrees. So how do you avoid sulfur formation or sulfur dioxide formation in the economizer? Is for Bosch we have a feed water preheater. So as the water is leaving the feed water tank, it will go to the feed water preheater, which will heat up the water to around 130 degrees before flowing into the economizer. This way you avoid taking water that is at a low temperature into the economizer, and therefore preventing condensation happening in the economizer. So that's how we avoid sulfur dioxide formation in the economizer. I know it's a big problem, especially for sites where you're having raw water, very cold water flowing into the economizer, which causes condensation. So for Bosch, we have a preheater between the economizer and the feed water tank.
Thank you. We can proceed. There are no more questions.
Thank you, Anthony. So what we have currently on the screen is a chart just showing energy usage inside a boiler. So condensation losses, which is the first one, is usually quite tricky depending on the fuel that you're using to actually utilize it. Okay, useful energy, that is quite good. Distribution losses, this is in the how you've cladded your pipes, how well is the boiler cladded, and so on. Then you have the system losses. This is inside the boiler. And then we have the flue gas losses. Okay. And as we go forward, I'll try and explain and see how we can actually try and recover a majority of the losses and try to turn it into useful energy. Okay. So just on your screen also on your screen on the bottom left, you'll see an example of natural gas with a dew point of 55.6, which ideally, as you have communicated before, we avoid condensation inside the economizer. So ideally, if you're burning natural gas, will not cool the water that is flowing into the boiler using the economizer below the dew point. Okay. Next slide. Okay. So, and this is the first. So apart from just the normal economizer, there is a second economizer called a condensing economizer. So as you can see on the setup, we have the boiler itself. We have then the economizer, the normal economizer, number 5. Then we have a condensing economizer, and there, I think that also other 2 new accessories added. There's number 6, which is the condensate neutralizer. Number 8, which is a pipe, ideally just going to a blowdown expansion module or drain. So condensing economizer, what this will do, okay, after you've passed your flue gas into the normal economizer with whichever fuel, if you're using let's say natural gas or so on, after the water has picked up some heat from the flue gas will still have some heat, and ideally you can take out some of the heat from the flue gas by use of condensing economizer. So here you will have water, which is feed water, either from an RO plant or a water treatment plant, flowing into a second economizer. So from the economizer, the water will flow into the feed water tank or a deaerator plant before going into the boiler or through the first economizer. Here you're saving around 5 to 7% of fuel just by picking heat from, say, the extra heat from the flue gas. Okay, so the difference between and just the normal economizer is that the condensing economizer, you're actually using water that is flowing into the feed water tank, while the normal economizer is you're using water that is flowing into the boiler. And next slide. And for the condensing economizer, the water doesn't have to flow into the boiler. The water can be used, the heated water can be used for process downstream. So in this setup, you can see water is flowing from, let's say, water treatment plant into the condensing economizer, number 2, and flowing into water heating or heating processes into the plant. Okay. Next slide. Before we go to the air preheater, any other questions? Hello, Anthony, are there other questions?
No questions.
Okay. Then the next savings potential when it comes to efficient energy steam generation is air preheater. Okay. We had this discussion previously where someone will ask, why am I heating the air that I'm going to burn? So just to explain the setup, so here you will have feed water coming in from a pump or a feed water tank flowing from number 7, you can see. Then you'll have a 3-way modulating valve. Then you will have an economizer 6, and then you will have air preheater, which will the main components. Number 2, you'll have your blower motor for the burner. Number 3, you have your air supply as number 4. Then you have a temperature controller, number 9, which will control the 3-way modulating valve, and then you'll have your stack and your boiler. Okay, so here water will flow from the tank, feed water tank or feed water service module through the pumps and through the 3-way valve. So the 3-way valve will actually determine how much of the water is flowing into the economizer of the boiler and how much water is flowing into the air preheater. Just a point to note that the assumption here is the water that is leaving the water service module is leaving from a full deaeration plant. That's why the temperature at entry is 103. Around 30% will flow into the air preheater. So in the air preheater, we have ambient air flowing in at around 20-25 degrees and leaving the air preheater into the burner at around 80 degrees. Then the water will recirculate back into the economizer and mix together with the water that is flowing directly from the pumps into the economizer, which is around 70%. And here the water again will be heated up with the economizer up to around 135 into the boiler. The benefits of using an air preheater in this setup is once you have cooled down the water around 30%, you have dropped down the temperature from 103 to 65 degrees. Thereby, you have reduced the temperature of the feed water tank, feed water temperature. With that, you have increased the gradient for heat transfer. Therefore, you're able to extract more heat with the economizer from the with the economizer. And again, another benefit is you're able to heat up the air that is flowing into the boiler. Another loss that you're going to look later on is by increasing the temperature of the air that is flowing into the boiler, you reduce the amount of losses that you get during preventing or purging process when the boiler is starting up and so on. So therefore, you'll be saving around 2% of fuel just by preheating the air that is flowing into the burner. Okay, next slide. Slide. Okay. Then another option for saving potential is cooling the feed water. So here, once you have a setup with 2 heat exchangers, so one is the economizer, which is number 2, and then we have a feed water cooling module, number 1. Then we have the boiler itself, the feed water tank, and a 3-way modulating valve. With this, you'll get around 1.8% saving potential. And again, here how you're saving energy is as water is flowing from your treatment plant into the feed water cooling module, it cools down the water that is leaving the feed water tank flowing into the boiler. Reasons for cooling down the water is you're trying to increase the temperature gradient against which heat transfer happens. So here, instead of taking water at 103 into the economizer, you're taking water at 65 degrees, which is able to pick up more heat compared to water that is flowing at 103 into the economizer. This way, you're able to pick up more heat from the or maximize your economizer. Okay. Just a point to note again. Here we assume the feed water tank is under full aeration, and it's a completely pressurized tank. So therefore, as you cool down the water, you will not have reintroduction of air into the water. Yeah. Anthony, are there questions?
Yes, so there's one that says, or Matthew is asking, please confirm if you'll be talking about your valves at all.
I think, Anthony, I think this is a question onto you on your side.
Spirax-Sarco valves, then those ones we will be able to mention them,
Yeah,
or we'll be able to discuss about them.
Yeah, I can sort of answer that. So on our section, we try to make this training is to pass on knowledge more than product. So we try to be as generic as possible. There is sometimes where we can only mention our own products because we know them best, and where they are, we'll speak of them there. Again, that's the emphasis here is trying to train you guys as best as we can and pass on generic knowledge so that it applies to anything you can buy in the market, not just our product ranges.
Thank you.
Thank you, Anthony. Okay. Then the second part of efficient steam generation will be how do you optimize the burner side. Okay. Nick, you can go to the next slide. Okay. So on the burner side, there are three main points of areas of optimization. The first one being speed control, second section being the flue gas side, it's O2 control or oxygen control, CO control, and then the last part being purging or preventing process during burner startups. Okay. Next slide. Okay. So on the first topic, speed control. So in most cases or most scenarios, you will have a burner that has a motor which is driving a blower fan. Usually, most burners will not have speed control. What does speed control do? Speed control will go to match the air demands of the burner to the speed of the motor. Okay? Therefore, you're able to get the correct amount of air depending on the burner load. Okay? Just by having speed controls on the blower fan, you're able to save around 75% of energy use, because there's a lot of wastage of energy of the blower and motor just by using dampers to choke the amount of air that is flowing into the boiler. So as on the right, you'll see a curve of bearing speed control and throttle control. And you can see the speed control will actually use less power when you're actually modulating the burner. Okay. Next slide. Next slide. Okay. Okay. So the second part is O2 and CO control. So CO2 control will be actually a probe installed on the flue gas on the exhaust side of the boiler, and this will actually monitor the amount of oxygen or excess oxygen that you have on the flue gas. Just going back to the first topic that we had, where we had the formula for calculating losses on the flue gas. As you saw, having excess oxygen increases the amount of flue gas losses. So the O2 will actually limit the amount of excess oxygen. Then the second point being CO control or carbon monoxide control. This will also regulate the amount of oxygen that you are providing into the combustion process. And ideally, you should, for complete combustion, you're not supposed to have any CO in the flue gas. So O2 and CO control will actually, if you have both in your burner, it will actually be able to monitor the conditions of the flue gas, and in most burners, it will be able to correct the burner curves for the burner, therefore having a more efficient combustion process. Next slide. Okay. Yeah. So there are variances which ideally during combustion, which vary. The first one being the fuel, can be the calorific value, the density, the viscosity. If it's gas, it can be the gas pressure, the ambient temperature, or the pressure of the fuel. The combustion air has different temperature, different density, different humidity levels. Then you have different burners having different efficiencies, and also we have flue gas challenges. Okay, on the right you will see a graph of the amount of O2, where the first graph showing burner with no control. So this is just a burner with nothing monitoring the combustion system processes at the end. So as you can see, the amount of excess oxygen is a lot. Just by adding O2 control, you're able to drop the amount of excess oxygen in the flue gas. And by adding CO control, you're able even to drop the amount of excess oxygen on the flue gas even further. Okay, so having both O2 and CO control, you're able to optimize your combustion process. Okay. Next slide. Okay. So here is an illustration just showing how a setup with an O2 control would look like. So you will have a probe after the economizer before the flue gas flows into the chimney. You will have a control probe which will send signals to the burner, and so this is how a setup for O2 control would look like. The next slide, you'll see a setup with both O2 and CO control. So here you'll have two probes in the connection within the chimney or the stack and the economizer. The probes will be able to monitor the amount of excess oxygen and CO in the flue gas and be able to correct the burner curves respectively. Okay. Any questions, Anthony?
Yes, we've got 2 questions, 2 more questions, and the first one will be, what is the best location of the economizer? If on the chimney, where exactly?
So the best location for an economizer, there are 2 types of economizer. There's the integrated economizer, which usually comes as part of the boiler. Then there's the second option, which you have a standalone economizer. So the first one will be the best location of the economizer, which is integrated with the boiler. Why? Because here you have its first advantage is because it's modular and it's compact, so less space. Then the second part is the quality of cladding and also the amount of cladding required is reduced. Then also the heat loss surface is reduced, so you have an integrated economizer, which you're going to see later on. Exactly. So the economizer, then on the second part of the question, the economizer is not part of the chimney. Usually it's either part of the boiler or in an integrated setup or a standalone. So you will have a setup where you have the boiler having a connection from the boiler to the chimney, a boiler to the economizer, then an economizer to the stack or chimney. So those are the 2 setups.
Thank you.
And any other questions?
Yes. The second question is, instead of cooling your feed water, making sure it is as hot as possible wouldn't help achieve better efficiency, as you would require less fuel for heating?
Okay. So Nick, I don't know if you can go back to that slide.
Yeah, just tell me which one it was, sorry.
Just go back. Still go back. Go back. Yeah, go back. Back. Still going. I think you're not. I think it's the previous slide to this. Slide.
Sorry.
So it's the second slide before we start the second topic on the banner. Where we're cooling down the.
This one. Sorry. Is that the correct slide, Alvin?
And not really. Let me just try and explain. So the reason why we're cooling the feed water before going into the boiler is you're trying to increase the gradient for heat transfer. So just a case in point, if you're trying to, let's say you're having a full deaeration plant, water is leaving at around 105 or between 105 and 103, and the water that is leaving the economizer flowing into the boiler is 130. Okay, so the heat transfer gradient that's just between the 2 is around 27 kelvins. But if you reduce the feed water temperature, let's say to around 65, just by doing that, you have increased the gradient. Yes, you're going to get less temperature of water flowing into the boiler. Let's say 116. But by just reducing the feed water temperature, you have increased the, let's say, the heat transfer gradient from 27 to 51. How did I get to 51? So after you've cooled down the feed water, after cooling it down, you heat it up a little bit to around 65 degrees. And so you're having water flowing into the economizer at 65 degrees. And after the economizer, you get water at 116. Yeah. I think, Nick, it's 8 slides behind this one.
I'm also a bit wary of the time as well, Alvin, just because
Okay.
it's 10 to 12.
Yeah. Then any other question?
Yes, another question coming from Brian. Yeah? So he's asking, using the speed control method, how does one ensure complete exhaust of flue gases once the motor speed is reduced?
So using a speed control, so the speed control will actually kick in during combustion as the burner comes on. So here you will still have your pre-purge or purging, preventing, where the blower fan will come on at full capacity. Make sure that there is no residual gases in the combustion chamber or the fire tubes, and blow out everything. So this does not affect the startup process. So you'll have your normal startup process, and then the motor will be reduced to the appropriate speed for optimum combustion process. So the speed control actually kicks in when we have combustion. Okay. Are there other questions, or we can continue?
You can continue. There's no other question. Thank you.
Nick?
Was it there?
Okay, so we're on, I think, next slide. I think in the last part on the burner itself, we have the purging process. Ideally, a burner should have the least possible start stops in an hour. Okay. By reducing the amount of start stop in an hour, you actually reduce the amount of heat that you're actually wasting. During the pre-purge process, the blower fan will actually come on, force air into the combustion chamber and out of the chimney, to ensure there is no residual gases or risk of backfiring. Then the burner will come on. So by reducing the amount of start stops, you're actually reducing the amount of heat that as the air is flowing into the combustion chamber, the amount of heat that is being picked is a lot, which can be saved. Just taking for example with a 5-ton 10-bar boiler by Bosch. Take for example, you're running a 10-bar steam system. The temperature inside the boiler will be around 184 degrees. The ambient temperature will be around 24 degrees, and you have a pre-purge of preventing ventilation process for around 30 seconds. Okay, we assume around 50 degrees temperature gain by the time the air actually gets into the combustion chamber. And if you just plug this into the heat transfer equation, you get this just by reducing the amount of start times from 10 start stops in an hour to around 2. You save around 2,200 euros per year. Okay. Next slide. Next slide. Okay. Then the third topic I want to look at is on conduction and radiation losses. And the first part, I just want to pose a question to everyone in the team. If you have a boiler, what is the quality of the cladding that you're using? And then how thick is the cladding? Okay. What is the condition of the cladding? And what other heat loss points do you have around the boiler? So on the slide, you have a boiler which has not been cladded yet. As you can see, the cladding there is around 100 mm. And you have a small I'd say contact point where the boiler shell will actually get in contact with the boiler frame. Just by reducing the amount of contact the boiler shell itself have with the frame with the boiler, you reduce the surface of heat transfer or heat loss. Okay. Then the second part is having good enough cladding. You reduce the amount of conduction losses from the boiler shell. And next slide. Slide. Okay. Then the second part is about insulations. So just tying back into the earlier asked question about the economizer. So the picture on your right is a boiler with an integrated economizer. As you can see, the amount of heat loss surface is quite reduced just by having the economizer integrated with the boiler. Okay. Next slide. Then another topic I'll have to cover is losses when it comes to water, the water side and condensate side. So the first one is being desalting, the third one being vapor steam, and then the last one being condensate. Next slide. Okay. So here we have a desalting line, condensate. So here usually boilers will have Bosch, that is, will have automatic desalting, or some will have manual desalting. The question is, after you've done desalting, usually your water or steam, flash steam, is leaving a boiler at a very high temperature. With this process, if you're able to recover heat from this desalting process or the blowdown process, you're able to recover some heat from the water that is going into the drain. So here you have a setup from the blowdown and desalting valve. You have the water flowing into an expansion module. Here, this will recover heat by heating up the water that is flowing into the makeup water tank or the feed water tank, and thereby you're trying to recover heat from the desalting and blowdown water. Next slide. Then the other way of saving energy is vapor cooling. So during the deaeration process, you will have some flash steam or some bit of steam or hot air that is leaving the deaerator and flowing into the exhaust. So you can also save around 0.5% of fuel just by cooling the small vapor that is leaving the deaerator and heat and hot air, and you cool this by passing the hot air into a heat exchanger, which also has water from the treatment plant before going into the deaerator. Okay. Next slide. Next slide. Okay. Then the other way of saving is by having condensate service modules or condensate recovery modules. So here, after the steam has passed through the whole plant and it has been utilized in the different plant processes, where does that steam go? Okay. So ideally, all steam should be, or the condensate should flow back into the boiler. Nick, I think, has spoken about this on previous trainings on the importance of saving condensate and how to actually properly collect condensate and pump it back into the boiler. So here you have a setup of two boilers. So feeding the plant, then you have the condensate service module into a deaerator plant, then the water flowing back into the boiler. This way you're saving energy, you're saving on the amount of chemicals that you're having to treat fresh water every time that you're putting it into the boiler. Next slide. Next slide. So there are two types of condensate tanks. They're usually the open air, which is not really advisable because if you have an open air condensate tank, you're actually losing a lot when it comes to flush them. So a fully cladded condensate tank is usually advised. Here you reduce the amount of losses in terms of water and heat, the amount of chemicals that you're consuming when it comes to treating the water. And by reducing the amount of chemicals, you're also reducing the amount of blowdowns, or how many times the boiler has to desalt. And thereby, you're also reducing, just by having good quality water, you also reduce on corrosion potential of the system. Okay, next slide. Then another aspect of saving potentials is water analysis. So I'll pose also another clerical question. Do you know the quality of the water that you're using in your boiler? How often do you measure conductivity, TDS, especially pH? So you can have a system where you have continuous monitoring of the water that is flowing into the boiler, and you're able to determine where you have contamination. Might be from the condensate, might be from the feed water tank, and so on. Next slide. So in this setup, you have a system where you have a water analysis module with a system control. So the SCO with the system control to control the two boilers below. So you have probes in the feed water tank measuring conductivity and turbidity of the water. Okay. Next slide. So this is only for monitoring purposes. Next slide. And in this setup, you will have same a system control with probes around boilers and together with the feed water tank. Then, as you can see, there are two treatment chemical treatment plants next to the feed water tank for O2 and pH correction. So here, the system control will monitor the different parameters of water at the different aspects, and it will be able to control the amount of O2 scavenger and pH correction chemical that you're using in your boiler. Anthony, are there other questions?
Yes, there's one that it's a comment, basically comment on wood fuel boilers energy efficiency controls.
For wood fuel fired boilers, first of all, Bosch does not do biomass boilers. Then when it comes to efficiencies, there are aspects of when it comes to ensuring efficient wood fire boiler. One of them being the economizer. You can have the condensing economizer. You can have water monitoring. So most aspects that are found when it comes to fuel fired or gas fired boilers can be applied on wood fired boilers. And next slide.
Okay, we can proceed here.
Next slide. Okay. So here is just a summary of the energy savings potential across the boiler room. Next slide. So just to summarize the presentation, you can have up to 7% fuel savings just by adding economizer, 7.5 savings on fuel by having a condensing flue gas economizer, 2.5 on air preheater, 1.8% on feed water cooling, 1% on expansion module, 2.5 on O2 CO control, around 75% of electricity costs on just controlling the speed of the blower fan, 0.5 on the vapor cooler, around 12% on high pressure condensate systems, then 8% on correcting damage or insufficient insulation. Then the last part is 3% on fuel, just optimizing by your control and regular service and maintenance and cleaning of the boiler. With that, I would love to hand over back to Nick.
Okay, yeah, thank you. I'm just trying to catch up with the slides. I think we could do another one of those. So welcome everybody. Thank you very much, Alvin, for Bosch as well. It was very interesting. So as many of you already know, the reason why we invited Bosch is we don't actually make boilers, we do the equipment around it. So Alvin, thank you for your insights on the actual boilers themselves and how to improve them. So I'm going to rush through the very beginning part of this to make up a bit of time. Who are Spirax? So again, we have many different offices. We have 145 operating companies, 180 local sales offices, 55 countries served by distributors. And I checked the figures, I've updated these since last time. We have over 10,400 employees now, of which 2,000 plus, which are local service. Skip some of this. Underneath the group, we have companies such as Gestra, which many of you would have heard of. Watson Marlowe, companies that deal with our electronic solutions, Chromlux, Thermalux, and Spirax-Sarco sits underneath the steam specialties business. We were founded in 1888, so we've been here for a while. We're a FTSE 100 company, which means we're in the top 100 companies in the share market in the UK, and have about a turnover of 1.4 billion. That's in pounds per year. Services we offer, many different product ranges, as you can see from there: flow metering, heat transfer solutions, humidification. We do valve reconditioning on our services. We do health and safety compliance, installation and commissioning, and various others too. And the reason why we know boilers is because we actually use them. This is sat in our training centre in the UK. As you can see, it has many of our pieces of equipment on it. We run a boiler, so it's not just theory to us, it's practical. So first off, we're going to talk about boiler house design. So a boiler house, or the energy house or energy center, comprises of many different items, many of which were covered by Bosch kindly. All the blue pieces of equipment there are things that Spirax can supply, but we still have knowledge and an understanding of everything in the boiler house too, so that we know how our products work correctly. So we call it a loop. So the reason why we call it a steam loop is because, as you can see, steam comes out of the boiler, enters your process. In this particular case, it's a heat exchanger, then via traps and condensate lines, then returns back to your feed tank, and the process begins again. So properties of steam. Why do we use steam? So it's a compressible gas, which means you can make pipe work smaller, depending on pressure, of course. Direct pressure and temperature relationship. So the higher the pressure, the higher the temperature, which means that it's an increase in enthalpy. So the heat that will be, the latent heat that will be given, or the energy that will be given to whatever you're heating or using. And it's higher heat content than hot water systems. So as you can see there's the figures with delta P's. So on this particular case, you've got a 4.19 kilojoules per kilogram of water, and you have 2,200 kilojoules per kilogram for steam. Steam flows with pressure drop, and there's no need for circulating pumps, so it's what we call a pull system. So by steam collapsing downstream and creating a vacuum, it pulls fresh steam from upstream into fill the void, so there's no need for a pump. And a uniform temperature gradient, so we know how much heat it loses over a certain distance of pipeworks at a certain thickness, so it makes it very easy for us to calculate and work out the heat losses from your system. And the heat transfer coefficients are often 2 to 3 times higher than water. Again, talk about latent energy when it's condensing. So as the steam condenses, that's when it gives off its heat. So as we said, there is a link between pressure and temperature. So on this particular case, 10 bar is just under 0.2 volume kilograms, meters squared per kilogram. If we are to lower the pressure, as you can see here for 2, we've almost trebled the volume that the steam takes. So that's why when it comes to supplying steam around a system, until you get to the point of use, we try to maintain as high a pressure as possible, because it allows us to use the smallest pipework possible, which reduces costs. It's also about heat losses and things like that. So we should be only reducing pressure at point of use, so the last few meters effectively. And as you can see, we see a lot of venting otherwise. So superheated steam, so everything on that line, as you can see, is steam. That's it means it can effectively be condensate at that temperature around steam. Below that line is going to be water, and above that it means you've added more energy to it, so it's become superheated, so it's become drier. So in this particular case, you can see that at 10 bar, we have a temperature of roughly about 184 degrees for steam. And at 2 bar, it's about 130 odd, I think. So boiler house, again, we're saying it's part of the larger system, so you may have many, many things upstream. So in this particular course, we're talking about the boiler house itself. And forgive me, I can't see my notes. So as you can see here, atmospheric feed tanks, if we talk about those, we have deaerators, which are quite generic, as Bosch can offer as well. The way they work effectively, as Alvin's already covered, is to preheat the water to try and create as much efficiency in the energy in the water that's being supplied to the boiler. So As you can see here, the elevated temperature is possible. Normal feed tank tends to be around 85 degrees. The higher you can raise that up to about 103, 105 degrees, reduces the oxygen, therefore reduces the need for chemicals, or reduces the need for as much chemicals, I should say. You will still need some. And then it effectively that has knock-on effects on your system. If there's less air, there's less carbonic acid. If there's less carbonic acid, there's less wear. So pipe works last longer, equipment lasts longer. And it provides energy savings because if you've got hot water or hotter water going into your boiler, you're not cold dosing it. And when I say cold dosing, what that means is if you have a water temperature entering the boiler, which is much lower than steam temperature, you will, for a split moment or for a short moment, you will stop your boiler producing steam. So the idea, as Alvin touched upon, is if you can supply that via a modulating pump where you are slowly trickling in the water, the difference in temperature, the volume of water that you're pumping from a different temperature is smaller. So there's less of a thermal shock to the boiler. So it has the ability to lessen the time that it takes for a boiler to heat up. Is there any questions at this point? Because I know I've kind of moved quite fast through that section.
Yes, and actually this may be directed to Alvin. Basically, a question from or a comment from Brian. He says, comment about steam generation heating methods of electric boilers. In brackets, he says, only remember the electrode type and give the advantages.
Sorry, Nick, to interrupt you.
No problem.
Okay, so when it comes to steam generation using purely electric, there are two types. There's the electrode type and immersion type. So the electrode type has its own advantages when you're talking about higher capacity boilers. One reason being is because you have the electrode immersed into the water, and if you don't have properly treated water, you have a lot of deposition or accumulation in the electrodes, therefore reducing the efficiency of steam generation. So electrode types are a good option when you're producing steam at higher capacity. Let's talk about around above 20 tons. But for small capacities, I would advise for immersion type electric boilers.
Yeah, so is there any other questions as well, Anthony? Or?
No other question, so we can proceed. Thank you.
No problem. Thank you for that as well, Alvin. So as we were talking about with the feed tank, so again, this just kind of reiterates that the cold pre-treated makeup water enters at high level, so the gases are driven off. This means that we're trying to remove the oxygen by creating the deaerator head, and we're preheating the water that's going in there. You can see that on the right-hand side of the tank, you have a recirc system. The reason that the recirc system is there, sorry, I'll just try and see if I can. The reason why this system is here is because what you will find is hot water will rise, cold water will sink. The recirc allows it to go back into the header and get some of that energy, but also to evenly spread the heat in this water, so that when you do pull down to your boiler, there isn't a cold spot at the bottom of this, so you're getting the ideal temperature throughout the tank. So as we were saying, it operates within a temperature range so that the chemical dosing can be regulated. So if we know what temperature this water is because it's tightly controlled, it allows us to accurately dose the chemicals into our tank because they will be rated to a certain temperature, a gradient of temperatures. Steam injection, again, maintains the operating temperature. So you can see it there in the red. And condensate returning at low level as it's oxygen free. So we're bringing the condensate in lower Yeah, so that we're not exposing it to air. And direct steam injection, yeah, for insulation, anti-stratification pumps, and so on. I'll kind of breeze through that, but if you have any questions, please add them, and I will go back. So again, a typical layout, as very similar to as what Alvin was showing. So you have your feed tank here, your feed water line into your boiler, coming off an economizer. So it's preheating the water through the economizer back into the boiler. Spirax-Sarco don't actually sell economizers, but we do know the process. So need for level controls and alarms. So what we're looking here is a horizontal fire tube boiler. So it's called that because of it's basically a cylinder full of water laying on its side with a combustion tube or combustion gases running through a series of tubes inside the shell. So here you have the burn tube, yeah, and your pass tubes. So you have your burner coming on, there will be a purge cycle as it heats up. Then the flue gases make its way through the passes and out the chimney. So steam here is being supplied at 185 degrees. And these boilers can have anywhere between 1 or 4 passes. So this can go 1, 2, 3, 4 times. And tubes can chamber where the tubes turn 180 degrees can be surrounded by water exposed to the shell. So effectively that means it's about a dry back or a wet back. So in this particular case, you've got a dry back. I think that's right, is it? Yeah. Which allows you for your pass tubes. This example, we describe a boiler with 3 passes. So we're going to be talking about 3-pass boiler here and a wet back. Sorry, that's a wet back. So here you can see you have enough water covering the fire tubes. So we want to cover this area here. If the water level drops below the flame tubes, this is when it becomes dangerous. The tubes begin to melt and crack. So what will happen here is the heat isn't transferred into the water, isn't dissipated. So that's when it becomes dangerous of collapse for the fire tube. So that's why level controls are very important to us. It's also because we want to get as much heat out of this as possible. If we're transferring it through the tubes, we want to capture that energy in the water, not just allow it to disappear. So flash steam blows the burner out and then thrusts the boiler forward. So the boiler water enters the flame tube and flashing off and expanding rapidly. So this is what happens when a boiler collapses. So what you find is if there's a hole into here, boiler would be put out by the sudden inrush. That high pressure water at high temperature would then expand in this tube, and it can cause a kind of an explosion via implosion. So that's why we need to make sure that these boilers are well treated and well looked after. So if this happened at 10 bar, for instance, yeah, the pressure released there would be quite large. So as it shows here, we need level controls and alarms to make sure it doesn't explode. Of course, a sudden release of the energy would be catastrophic. Fortunately, modern day boilers have a number of different safety mechanisms to prevent this from happening, and means that catastrophic incidents are very rare. In areas where water treatment is not so considered, obviously it's more common, but still globally it's a rare occasion. But it does remind us of the importance of looking after the boiler house and doing our risk assessments and making sure our boiler is running as efficiently as possible. So again here, the reason why you need accurately control is also for efficiency. So as you can see, the area of the water where it's flashing off is here. So your steam is being produced here. By being at this point in the circle, you have a larger area, so you're releasing more steam. So it's the ideal position for this heat release to happen. Modern boilers are smaller than, say, 50 years ago, so they hold less water and therefore they need to respond to demand quickly. So the reason why they're smaller is that they become more efficient. It means that they need to, because of the capacity that's held here, they need to be able to act fast. So modulating pumps, the various controls that Alvin was touching upon, all of this helps the boiler respond quickly. So as it shows here, if you have a water level that's too high, the area available here and the space available for steam is much smaller. So the surface area to steam off is smaller. So we try to maintain this level at a fixed point, so it's not too high, but it's also not too low. And this means we get the best quality steam. So we avoid erosion, corrosion, water hammering your pipes, and inefficiency because the steam has less energy because it's wetter. Is there any questions at that point? Anthony?
Yes, there is a question.
Yeah.
From Abdi, and says our steam traps are Spirax-Sarco made, but it failed within less than 1 year. Can you please share as a contributor for the failure, I believe?
So it depends what kind of failure it was. I mean, traps can fail open or they can fail closed. In some extreme scenarios, you can have acid buildup, so that you find a point in the trap channel which has become to leak. So if you kind of be able to direct us a little bit more on how they failed, I can be more specific. But as a general rule, it tends to be for a few different reasons. So if you've got a wear and tear from acid buildup, acid tends to be formed that you have air entering a system before the trap, and you also have a higher than normal velocity through the trap. So that added velocity where it hits corners, plus the fact that you've got a carbonic acid there or acid buildup, wears certain trap materials faster. So if you've, say, got an SG iron trap or a cast iron trap, you'd see that fail quicker than a carbon steel or stainless steel. Other factors can be dirt in your line. It can be sort of from your carryover or badly maintained lines can block traps, causing them to fail open or fail closed, depending on where the dirt decides to settle. Water hammer can affect particularly ball floats, because when water hammer hits the float, it can compress it, so it crushes the ball. Therefore, that sinks, so that the trap fails to open anymore. In other countries, not so much Kenya or Africa, you've got freezing, which can cause an issue in winters with traps, because you have to be able to melt that ice. But also, as the ice is expanded, it damages the internals of the trap. If it is of help, next month is actually about traps. So we'll cover the pros and cons of different types of traps and how they fail as well in the next webinar. But if you have specific questions, our contact details are, I think they're shown towards the end. So please reach out. I'm happy to go through your specific failures. So any other questions?
Yes, thank you, Abdi. I think what we'll do is we can get in touch with our sales engineer who would like to investigate the specific failure mode that you've had, so that we can be able to interrogate and come up with a solution for that. Yeah. So I believe you can please get in touch with us, and then we'll be able to follow it up on for you. The other question is coming from Brian, and basically the question is, what is the best and most efficient way of pure steam generation? That is, using heaters or using indirect heating of RO water with plant steam?
So I'm actually going to pose that question to Alvin, because he's a boiler manufacturer. It will also depend a lot on the style of the boiler you have. But Alvin, can you grab that?
Thank you. Sorry again. So for pure steam, the best method will also be dependent on, I said, naked hinted, the setup, whether you're using heaters or you're using process heat. So it's usually dependent on how the setup is. So there is no, let's say, one rule fits all.
Thank you, Owen. Yeah, I mean, for instance, if you've got a fire tube boiler, they're more steady, they tend to produce a lot more steam. But if you want superheated steam, you'd use a water tube boiler. So it depends on your process. There's different type of boilers for different processes. We also have you have electric, you have biomass, you have different fuel sources, and they act differently as well. So biomasses tend to be very slow and steady. They tend to be quite knowable, but they don't react very fast when it comes to changes. So again, it's very dependent. If you have a specific question, we can certainly address that if you get in touch with us. Both myself and Bosch's details will be displayed as well. So we're willing to answer your specific questions. Thank you, Arvin, as well. Any other questions, Anthony?
Okay, no more questions. We can proceed. Thank you.
No problem. I love these questions, so keep them coming. Thank you. So we'll talk about level controls. So accurate and reliable level controls are essential for both safety and efficiency of your boiler. So you will need to know the water level at all times. And first level control and safety feature on the boiler is the gauge glass. So many of you would have seen there is somewhere on your boilers, there is a visual ability for you to check the level that is in your boiler. Their purpose is to allow the boiler operator to have a very quick and reliable visual interaction with the boiler. So without having to check anything too difficult, he knows instantly when he walks into that boiler house on how safe it is and the relative position of the water in that boiler. So we'll start off using the gauge glass to demonstrate how rising and falling water level during various different stages of steaming can affect boiler operation. And hopefully, so you can understand the importance of why we need the control. So here we are likely to be a number of visual level markers on the level gauge. So you'll have your normal level, you'll have your pump off point if it's on off control, and your pump on point. If the boiler is fitted with on off pump controls, then the switch will also, there will be a switching mechanism there to turn on and off the pumps as well. However, if the boiler is fitted with modulating pumps, then this is happening at a constant constant rate. So with modulating, you would be maintaining one set position. With on-off control, you would pump up to one level, and then as it drops to a certain point, it would then turn on again. So you're filling, as you can see, there's a massive difference in volume of water you're adding to that boiler. So again, when we were talking about thermal shock, this is what we mean. So modulating would hold it at one point, so it's trickling. It's almost like having a leaking tap. On-off is giving a large volume of water into the boiler. So regards to audio alarms, they also would offer you a point where if you reach first low, for instance, you have an audio sound to give you an idea that there is a failure happening. It's very important on this. So the first low will be audio, and I think it needs you to come and reset it. The second one will actually turn off turn off and lock out the boiler. So as it says here, if you reach the second low, the alarm burner, then the burner locks out and won't fire, even if the water level recovers. So what I probably should have said there, first low is if the water then starts to rise because your pump kicks in, the audio alarm will stop and the boiler will turn back on. Second low means the boiler will lock out. So the burner will lock out. And it will not, even when the water level returns to where it should do, you have to manually reset. So that's very important. It's protecting the fire tubes and the pass tubes in your boiler from overheating and potential collapse. So these are very important controls. So whilst not usually required, many boilers also fit a high level alarm. So we were talking about the area for steaming. Many customers also fit a high level alarm, so it could be a failure where the pump has failed to stop. This means that you would eventually get more carryover. The area to produce steam is less, the steam percentage in the boiler is less, so it can be almost as harmful, although it's not a safety issue of the boiler exploding. It becomes harmful to downstream, where you've got more carryover, more chemicals, more everything effectively going down to your pipe. And so we should be able to identify all the boiler states and conditions by observing the sight glass or the gauge glass. But this only gives us a visual indication. We need to install level controls, control probes that are capable of monitoring the true water level. So again, because this sits on the side of a boiler, it will show a level, but it relies on it being clean, being blown down properly, and all those things. So we would still recommend that you have the probes. I think it's a legal requirement, the probes inside the boiler to give you your alarms. So as we can show here, you can either mount an external chamber. So many of you have Mowbrays. The Mowbrays tend to be like that. It's a float inside and it's set externally to your boiler. Or you can mount them directly into the shell. So in this particular case, it's our connectivity probes. So we've got our LP10s here. So as it shows there, you've got your pump off, your pump on, first low alarm, and on a separate, because they need to be independent, you have your high level alarm, which is a choice, the high level, but the second alarm, second low level alarm, again, is independent because it's on a separate probe and should be mandatory, or is mandatory, is to protect the fire tube on the boiler. Is there any questions at that point?
No more questions, so we can proceed.
Okay. So boiler level control, as you can see here, there's slowly running through where it's got the steam. So we need a high first low and a second low alarm, and then also a level control probe mounted in at least 2 chambers. So as we were saying before, you've got 2 separate alarms there. And that's so that they're independent. So if one fails, the second one shouldn't, and that keeps you added protection on your boiler. There are a number of different level types, level control types. Most popular being used are S&T steam boiler and mag float, conductivity, capacitance. Those are tend to be the standard ones in the market. So as mentioned previously, there can be quite a volumetric difference between the pump on and off controls and by modulating. So cold water being added to the boiler when there's a demand can cause steaming rate to fall, as we were talking about before, and during times of peak demand, and there is also a greater risk of carryover. So when you depressure this boiler because you've collapsed the steam, because you've cold dosed it, the water in it will expand, therefore it's able to carry over from your crown valve. So your crown valve being at the top of the boiler and into your system easier. So cheap, easy to install, and good for smaller stand boilers. One pump boilers. Lots of starts and stops on the pump. So when we talk about start and stop, it's easier on smaller boilers because you don't see so much of a change. But the bigger the boiler, the more essential it is to have modulating control. So modulating, as we were just talking here, as you can see, it's a typical setup. So you've got a capacitance probe, which is telling you the level. It will be set at a certain point. You've got your feed water control and your controller here and a feed water pump, so modulating pump. You also have a recirc, so when this closes, you don't deadhead the pump. So you want a small orifice pipe, so something that's maybe 1/4 inch, 1/2 inch, feeding back upstream, so that when this pump is stopping or slowing down, that there is a pressure release there, so you don't damage the pump. This is capacitance only as well. So element 1, so one element control and 2 element control. So as you can see here, 2 element control is level control and metered steam output, and suitable for sudden load changes. So if you have a high demand, plus or minus 25% change, this would be the best system to use. So as you can see, you have your capacitance probe here, your controller for your feed water. Element 2 is your metered steam. So, and that's going back to an interface unit, which is both receiving and telling what the feed pump to react. Is there any questions on that?
No questions?
No.
Yeah.
So 3 element, so metered flow water tends to be more for when you have more than one boiler, several boilers at a time. So it's the same as 2 element, plus you end up with metered feed water. So you're metering the feed water into the system too. And this gives you a more stable, more efficient and better steam quality. Must have modulating supply to it though. So here, blowdown. So you have your blowdown. Why do we blow down? So in addition to level controls, pumps, alarms, all those kind of things, we also need to test and blow down the boiler, which means it's maintaining the correct water chemistry within the boiler. When you end up with sludge at the bottom of a boiler, not only is that displacing the amount of water you can have in the system, but it floats around the system. It doesn't always sink to the bottom. It capes fire tubes, pass tubes, lowers their ability to transfer heat. So we regularly blow down a boiler. I think it's either once a day or once per shift is recommended. So steam users should always speak to the water treatment experts, because you want to know exactly how your water quality differs. So the requirements for the boilers and the amount of chemicals you need will change depending on the area you are. Chemicals and minerals that are present in raw water itself and the chemicals we add to the water will behave in 2 different ways. Some will solidify and make the particles fall as sludge to the bottom of the boiler, and some will be held in suspension. So that's what we mean when we say total dissolved solids. So both of these we need to get rid of. So regards to heavier particles or the sludge, we need to remove this. So in order to do so, we need to, so it won't come back and affect the heat transfer. We need to get rid of it, remove it completely from blowing down on the bottom. So many of you, I've been to many boiler houses, and quite often you see more than one key. The reason why we sell a bow down valve which has a removable key is we recommend there should only be one in each boiler house. So if you have 4 boilers, there should still only be one key. The reason being that prevents all 4 boilers from being blown down all at the same time. So it's a kind of a manual mechanical mechanism for you to protect your system by only having one key. Only one valve can be operated at a time. These are also set on springs, so you physically have to push the key down and turn it to be able to hold down the blow, to blow down the valve. That means that the key can't stay in there. So you can also have actuated blowdown. So it could be set to a timer where you're blowing down, say, once every few hours or so for a set period of time. Ensures that it's more accurate, because even the best operator in the world, unless he's physically timing it, there will be also a delay in the amount of time he's blowing down and the stopping or the turning off of that valve. So an electrical or pneumatic means of doing that is more accurate. It means that when you put in, say, a 30-second blowdown, it is for 30 seconds. It's not for 32 or 28. So it's the argument is that it's more efficient because it's more reliable. So therefore less waste. Again here, as we show, you've got the pneumatic unit, you've got a pneumatic actuator, which is going back to a timer unit. and that's giving the control signal for it to open and close. How are we doing on time? Yeah, I'm just keeping an eye. So bottom boiler blowdown needs to be collected somewhere. So in Europe, I think the legislation is similar in parts of Africa, but we can't blow down water to drain any higher than 43 degrees. So we need to put that somewhere to be able to cool down before we release it to drain. So that's where our bottom blowdown vessel comes in. So it's safety critical. It comes under, in the UK and Europe, it comes under the BG03 guidance for manufacturers' recommendations, and it's recommended that it's automated blowdown, so that you can make sure that not all boilers are blowing down at the same time. And it's a vessel, not a pit, so it provides a safe and correct and energy efficient blowdown. By collecting in a tank as well, it also gives you ability to reclaim that heat using various different types of heat exchangers, which we will cover at a later date. So these should be correctly sized. So again, you know how much blowdown is coming from your boiler, but if you've got 4 boilers blowing down the same rate, you will need a bigger vessel to be able to take all that before it cools down and is then being able to be released to drain. So yeah, and it can accommodate multiple boilers, as it says there, so individually connected and isolated. What that means is that on this manifold here entering into the blowdown vessel, there is a separate pipe for every boiler or everything that's blowing down. So we need to ensure that we have, if we have more than one boiler, we are performing blowdown at timed intervals that allows each discharge to be cooled down significantly before the next one. So what that means is that we need to space them out, that the blowdown vessel is able to cool the water that's within it, release it to drain before the next boiler starts its blowdown process. So the reason being, we don't want to overfill this tank. We don't want it to leak. If you overfill it, it will hit the overflow and it will go down to drain hotter than intended. So timing of the blowdown is essential. The TDS control. So again, we should be monitoring the TDS, the total dissolved solids. We can do that in various different ways. You can use probes, sensors to monitor the TDS. So we can release it timed. So you can say that it's set for every 2 hours, 3 hours, or continuous monitoring. So you have a set point where you are deciding to blow down when it reaches that set point. All these values will be found on the plate for your boiler. And it would just effectively drip through if it's continuous monitoring. So automated, again, it doesn't rely on an operator to have to watch it. You can sample it. So as you can see here, we have the sample cooler. So we can take a sample, we can check. So there's your manual intervention there, but the system itself is looking after itself. And it helps minimize foaming and carryover. So the more TDS you have in your boilers, the more likely you are to have carryover. So that foam is caused by the chemicals that you've dosed into your boilers, by the collection of TDS as well. So it is more likely to foam inside your boilers if the TDS is not correctly monitored. Is there any questions at that point?
Yes, there is. First one being from Brian. Unfortunately, Brian will not be able to unmute because of the way the Teams live event has been set. So I can only read the questions. And the question is, I have interfaced a boiler where the steel ball float was kept buoyant, even with the water level physically dropping until I throttled the valve on the water side of the tube connecting to the Mowbray float. This was irrespective of checking the tubes independently. What could this signal?
So it's an imbalance of pressure. So it's the only thing I can think of is an imbalance of pressure. You've got higher pressure at the bottom of the Mowbray than you have at the top. But it shouldn't happen because there's a blowdown procedure on the Mowbrays, just like there is on any other level controls. I would suggest to me a blockage of one of those ports. In this particular case, the top entry port. But Anthony, you ever come across anything like
I have not. Maybe Cornelius or Alvin, if you've ever come across such a thing.
No,
Not really.
I think it looks like it's a pressure thing. Unless we see it, it's probably going to be difficult to make a judgment.
Yeah, maybe what we can do is out of this call, maybe we can get connect to each other, and then we try to do an investigation on this. I think that would be the best course of action, Brian.
Yeah, the only thing I can think of is like I stated, it'd have to be an unequal pressure difference across the tube of the Mowbray. So the only way I can think that can happen is by a blockage on one of the ports. But again, if it's blown down properly, it shouldn't happen. I think you got the sequencing valves that should be able to make sure that you're blowing down those properly. Again, yeah, it'd be more interesting to hear more about that so that we can properly diagnose for you. It shouldn't be, they're pretty robust, to be honest, so they don't tend to fail often, but like anything, they can fail. So yeah, please get in touch afterwards. Any other questions, Anthony?
Yes, there's another question is, what is the limit for the TDS value?
So it depends on the boiler manufacturer. I think we use is it a value of 2,500? Is that what we state on our controllers? Anthony?
Maybe Cornelius can clarify on that one.
We use 3,000 to 3,500. Generally speaking, it's a fairly decent balance. Generally, with the boiler OEMs in South Africa, the boiler OEM would be able to tell you, generally speaking, on a packaged boiler, 3,000, 3,500. If it goes more than that, then you do start risking scaling. If you go below that, you do risk blowing down too much, and that becomes inefficient and costly.
Yeah, so thanks, Cornelius. So yeah, like I said, it will be on the plates for your boilers. As Cornelius said, we use as a standard figure, we use 3,500, but that can differ. It will depend on the plate values that you have in your processes themselves. And as Cornelius said, is to prevent forming of scale and things like that on boiler surfaces. So, for instance, to kind of add on to that, a 1 mil thick layer of scale can result in insulating efficiency which means it would cost you up to 10% more fuel because of the scale, so because of high TDS. And foam being drawn out of the boiler onto the headers and down into your system will stop the energy or lower the energy that's available in erosion, corrosion and water hammer in your system. Hopefully that answers that question. Anthony, any others?
No more questions. Okay, there's one that's just come in. And it's coming from Yusuf. I would like to know what is recommended if my feed water contains silica. I have been suggested RO prefiltration by some, but my water treatment provider says ultrafiltration will be sufficient. Furthermore, my automatic conductivity controller for the TDS blowdown has not been functioning for a few days. Can Spirax point me in the direction of the agents of these controllers and valves?
So yeah, if you get with the last part, if you get in contact with us about the equipment you have and the part numbers you have there, we can certainly look into it. If it's not us, usually we know the right contacts too. Regards to silica, so silica is a problem worldwide. It's becoming more of a problem because of the amount of plastics being released into water tables. There's best case, there's okay, and then there's not what not to do. So best case is always going to be RO, because the RO is going to be the thin enough filters or the fine enough filters to be able to capture it. But again, It will depend on the benefit versus cost. Cornelius, do you see a lot of silica in the water tables in South Africa?
It's not particularly common. We do have areas that are harder and softer water, but it's not a common problem in South Africa. But yeah, RO would sort that out, or potentially even a demin and a reman plant.
Yeah, it's always going to. I mean, RO is the standard go-to solution for those kind of things because of how effective it is. Again, that comes with costs. I mean, the higher the ability of something to perform, normally the higher the cost. So it's about balancing your what you will gain against the cost of what you're seeing. So yeah, again, yeah. So recommendation RO, but that doesn't mean that's the be all and the end all. Hopefully that answers that one. Is there any other questions?
No more questions. Thank you.
Okay, so I'm going to rattle through the next ones just because I've just seen the time. So here we have TDS.
Sorry, before you rattle, there one late question came in there. What's the best sensor to be used in the system for TDS control?
So we use conductivity, don't we? Effectively, yeah, it's conductivity or capacity we use. So as a standard, that's what we use. There's different ways of monitoring it, but Spirax has suggested that they're the best for us, at least. Yeah, hopefully that answers that one. So, is there any other ones that have popped in? No. Okay.
I think that's it there. Yeah.
Okay. So again, we're talking about heat recovery here. So Alvin touched upon the importance of it as well. So we want to make your system as efficient as possible. And the best way to do that is in this particular case, is by raising the heat of the water you're supplying to your boiler. So here we've got the TDS recovery. So you have your TDS is being blown down. It's then going through a trap, so it separates the steam and the condensate. We run it through a heat exchanger and use that to preheat the water that's then being fed into there. So you're heating this water. We then have the flash recovery, so the differential of pressure that's coming through here, and that's being fed into a de-aerator unit in this particular case. So we're trying to capture as much energy from that TDS, because remember that's at 10 bar temperature, yeah, so it contains the energy that you would be using normally to steam. So we don't want to just send that to drain and waste it. Good way is, as we said here, is the heat exchanger. So it reduces the loss. Hotter your water, the less fuel you need to be able to raise the temperature and so on. So daily tests, the tests you should be doing on your boiler is minimum. So all level controls and alarms, mounted external chambers, they should be checked. Standard, not high integrity. High integrity would be something else in controls. So regular basis should be checked on a regular basis to make sure they're working correctly. And really comes down to two things: how are you mounting the controls and the operating principles that are there. Weekly tests, all level controls, alarms, regardless of how they're mounted, internally or externally. So steam boiler daily control testing. So you should be, this again shows the Mowbray. So I think it was Brian that asked, the only way I could think that you'd get an imbalance in this chamber would be if this one was blocked. But again, that would have to be by the collapsing of steam or whatever else there, or cooling there. Please get in contact with it and we can speak more about this. So daily tests on this one, magnetic, you should be blowing these down using the sequencing purge valve, as it shows here. So as you turn this, it runs a certain different sequences, so it blows down the top, the bottom, both at the same time and so on. Again, I'm going to rattle through this just simply because of the time. Magnetic floats, so these again are daily control testing, so you want to make sure these internal ones are still working properly. So you need to make sure that they're blowing down properly, that they're controlling, that you're still getting a signal there. So you'll be manually lowering the level in the boiler, make sure they fire, so on. and conductivity probes. So again, this answers the question where you were talking about for the feed water on this particular case. So you're using conductivity there. Should be a daily test to make sure it's working correctly. It's not supplying the water, that this is turning on and off, or keeping a level depending on whether it's modulating or on-off control. You need to make sure that's working correctly. Please do not, you do not need to test the high and the secondary low controllers on a daily basis. So all you're doing is just trying to make sure that probe changes the flow. So weekly testing. This is undertaken by closing the feed water valve and then evaporating the water off until the level drops to the first alarm. So we need to check that the alarm sounds and that the burner switches off. So that's the important part on the first level, and that should be done weekly. So therefore, you're no longer producing steam. We then check the second low alarm is working correctly. So we would then lower the water again further until you reach the second alarm by manual means. And then that should sound the alarm and should lock out the boiler altogether this time. And that confirms our level controls, or level alarms effectively. So mass of water released during the weekly test is volume between the normal water level and the second alarm. So that's the total volume you're getting rid of. This is what the size, the BDV capacity on. So the blowdown vessel should be sized on where the running level of the normal level of your boiler, right the way down to the second low level alarm. That total volume is the size of the capacity for the blowdown vessel. So hopefully that makes sense. So again, we're talking here about common 4 boiler layouts, not recommended, because effectively you can pressurize the other boilers. This is far more effective, so you're breaking them into 2s, right headers. And 4 boiler design improved layout, so effectively it's saying that we're going into 1 header coming into the top, allowing for even compensation, even load from each boiler. And each should be fitted with a check valve. So again, this is where we're talking. If you have 1 boiler off and you don't have a check valve, the other boilers would pressurize it. So by putting a check valve in there, keeping the isolation, your crown valve and so on, things like that, you can make sure that that boiler is not only not wasting steam by being repressurized by the other boilers, but it's also safe to work on because it's been depressurized. It's safe to be able to open. So steam metering, as you can show here, gives you a true picture of your consumption. So it's always recommended that mass of the steam leaving your boiler house is monitored. So you want to know how it helps you with the efficiency of your boiler. If your boiler is rated to produce a certain amount, but your meter is saying you're getting less, then that gives you an efficiency on the boiler. It shows that it's less efficient for one. Again, I'm rattling through these. So arrangement 1 on supervision. So this is to do with the, so in the UK, effectively there's various control motor types. So we have safety features and testing criteria, meaning that a boiler house can be designed in these arrangement types, which in turn advises the level of testing and supervision that is required. So arrangement 1, manually mounted standard controls. Boiler attendant must be on site all hours of the boiler operation. So when that boiler is on, there should be somebody present. Arrangement 2 is with the high integrity controls and external chambers must be auto drain. So a trained or responsible person has to be on site all hours of operation. Arrangement 3, which is external chambers not permitted, so you can't have them, they have to be internal. Auto TDS, modulating feed pump controls and an automated boiler house. So effectively nobody would need to be present. I would say arrangement 3 is quite rare in Africa. So standards and legislation. So this again is more for the UK market. I know some of the European standards and British standards have been adopted throughout different areas in Africa. So this is more for a reference. As you can see, they have the guidance notes there if you guys want to look them up. So it's BS 2790 for Shell boilers. And you have BSEN, so it's both British standard and European, which is 12953 for Shell boilers. BSEN, again, British and European standard for water tube boilers. BS 2486 for water treatment. INDG 436 for safe management of industrial steam and hot water boilers. So again, that's more of a standard legislation. L122, safety and pressure systems, so it's the pressure regulations. And HSG 253, which is the safe isolation of plant and equipment. So I'll leave that there just for a second longer, just in case you guys want to make note. There will be local legislation depending on what country you're in. When there is a no legislation in place, which is rare, but you can always fall back on these because there is many boiler manufacturers around the world that not all of them, but some of them work to these standards. So again, more guidance documents. These are things that aren't necessarily law, but to follow them means that you're in compliance. So you have the BGO1, which is guidance for safe operation of steam boilers. BGO2, which is guidance safe operation of hot water boilers. BGO3, which is blowdown systems. BGO4, which is water boiler treatment, or boiler water treatment guidance. BGO5, guidance and design and operation of biomass boilers. Again, in sort of East Africa, that may be quite handy. BGO6, hot wells and deaerator guidance. BGO8, temporary steam and hot water boilers. So that's more for you guys that may be buying your steam per kilo. That would be classed as a temporary installation because it's removable. So that would cover you guys. And they're all based on EN 12593. So we're coming to the end now. If you guys have further questions, we have plenty of legislation and training documents and PDFs we can share. So please get in contact. We're able to supply a wide range of engineering books, both PDF and hard copy. I will mention the hard copy is harder to get hold of depending on where you are due to duties and various different things. But everything is available in PDF too. And it has been our pleasure to present to you today. So as you can see on the screen is all of our contact details. You have Bosch's to the left, Spirax to the right. Please send those questions through to us if we've not managed to answer them. We're going to briefly, I think we briefly have enough time to take any more questions that may be. So if you haven't sent one in already, please direct it at both myself and Alvin now, and we will try and catch those before the end of the session. So I'll leave that slide up there so you can still make note of our contact details. So Anthony, is there any questions?
Yes, we do have a question. From Fabian, what he mentioned, sometimes we face the issue of those dosing chemicals for boilers in order to get a good pH and TDS. What can we do when we meet such questions?
So it's going to be TDS control and blowdown control. So that's what's, I mean, the chemicals are dosed depending on your water treatment expert. It says what should be added. The only way to control the TDS in there is by TDS blowdown. So you have a TDS point. So as Cornelius was saying, that's a rough figure for us, a generic figure. We use 3,500 parts per million, and at that point we blow down. But the plate on your boiler will have a value where it should be blown down. And it will be dependent, but you're not going to go wrong by using 3,500 if you can't find it. And the blowdown, again, should be done once per shift or once per day. So depending on what's first. This will maintain the sludge inside the boiler. Alvin, I don't know if you have anything to add on that as well.
Yeah, you're right, Nick. So for us, TDS is again 3,500. But the lower the value for the boiler water, the better, because you have, if you have a system with automatic blowdown, you have less blowdowns.
Hopefully that answers that question. Is there any others?
Yes, I think, okay, from Brian, it says, what is the correct orientation of an LCV?
An LCV, so check valve.
Yes.
So I don't think there really is one. They can go as long as you've observed the way that the cap flap or the check part of it in the valve works. So you've got flow going from the right direction through. Doesn't make a difference whether it's with steam, especially whether it's horizontal or vertical. It still operate.
Yes, I think mostly for the DCVs it will be any orientation. For the LCV is mostly on the horizontal application.
That's the one that's got the more of a valve body, isn't it? So yeah, horizontal on those. The DCVs can be any kind of direction.
Yeah. Let me see. Okay. I don't think there's any other more questions. There's one question that I think we may have missed. How much energy can be recovered using blowdown vessel? I don't know if we answered that.
So it's very dependent on how much you're blowing down and the temperature that you're blowing down at. So if you've got a 10 bar boiler, the temperature is going to be higher than if it's a 7 bar. But as a percentage figure, I think we give a rough estimate. Antti, do you remember how much we say by recovering the heat from a blowdown vessel you can save?
6%, I think, on fuel.
Yeah,
but depends also.
Sorry, go on.
Depends just how much blowdown that you're doing.
Yeah, Alvin, does Bosch have an official percentage figure from heat recovery from blowdown?
So heat recovery from blowdown is around 6 to 7% on fuel. And yes, you're correct. Remember, the blowdown module does not only happens during blowdown, but also you also use it during normal operation during the desalting process. Yeah. And then Anthony, I think there was a second part on Fabian's question. So he also asked about how does he meet the correct values for pH and TDS. So we also do have guidelines on the quality of water that needs to be in the boiler, usually around pH of around 10. I think so. So there are some parameters which we should advise customers to meet, which are again based on the EN 12.93. Okay. So for you to be able to meet these parameters, usually we'll advise customers to have their water analyzed by a certified lab. Then a certified chemist will advise how much O2 and O2 scavenging and pH correction you need to dose into the water. So it's not also another lab where one fits all. It's dependent on the water analysis. Back to you, Nick.
Thank you. Thank you very much, Alvin. So is there any other questions as well?
No more new questions.
So again, thank you guys for all attending, and as you can still see, there is our direct contact details on the screen. Please feel free to use them, both Bosch and ourselves. We put them there for you guys to use them. So yeah, the more the contact, the better. Alvin, I don't know if you want to say anything before we close down the session.
Just want to thank you all for attending the training. If you have any questions, feel free to reach out to the team.
Yeah, again, thank you very much from both of us, all of us, and it's been a pleasure to present to you today.